we'll look again at how to create frequency tables and grouped frequency tables, and the differences between those two, right? So I'm going to just do little baby versions of these. Once you know how to do a baby version, the only difference between a baby and a big version is there's a lot more numbers to do it to. It's not like the process changes, right? So let's suppose in my first example that we collected data on how many siblings you've got, right? So that would be counting yourself, how many brothers and sisters have you got, right? Okay, and in fact, we can actually do that. If you hold on a second. Right, everybody here, if you look at the bottom right-hand corner, do you know you've got this little guy, thumbs up fella? See me using him right now? Okay, so I'm going to ask you, if you want to, you take part. If you don't, you just never answer the question, and that works. But I'm going to ask you to stick your thumbs up when we get to your family's situation. So we're talking about siblings here. So we're going to use some real data to create a frequency table, and then from there a histogram. And the data is going to simply just be, including yourself, how many brothers and sisters have you got? So we'll have to be specific about that because there are certain family combinations. So you will count yourself, obviously, so there's guaranteed to be one. You count a brother or sister, you count a half brother or a half sister. Do you call them half brothers and half sisters in America, or do you call them step brothers and step sisters? Well, no, half brothers is actually a different thing from a step brother, isn't it? Step brother would be a melded family. Okay, so you, brothers, sisters, half brothers, half sisters, but not step brothers and step sisters, right? I've just arbitrarily made that rule up. Okay, so how many of you is it? One child in the family and it's you. Okay, so I won't write that number down. How many are two then? You and somebody else. Okay, we got a two. And another two. Threes, how many are three? 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Have we any, Gracie, are you a 3?
Yeah.
Okay, so I think I missed you the first time. How many are 4? 1, 2, 3. How many are 5? I'll wait for somebody to disappear. Cool. 6, 7, 8, 9. Me, 10. Oh, you got 9, Jennifer? Oh, I just beat you. I got 10. Hey, me and you must share a lot. Isn't it nice having big families? Well, maybe you don't agree with me. Oh, so. I think it's great. I love being a part of a big family. Right, so this is what we would call our raw data. And it's not too difficult. They're not a lot of numbers, but can you imagine this wasn't just a small set? It was like 400 numbers, right? You really don't want to look at a page full of 400 numbers, even if they're in order, because it's quite hard to get any meaningful idea of what's going on, right? So we're going to create a frequency table. It has 2 columns. The first column,
we're not seeing your screen.
Oh, thank you for telling me that. I forget. And we're going to go click on this guy. Right. So here is the data that I collected. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So n equals 14. We have number of siblings, right? And we'll start with 2, 3, 4. And I know nobody said 6, but we still put it in. We still put in 7. We still put in 8. I hope I make this 9 and 10.
I said 6, but I don't think you counted me.
Oh, perfect. I'll just squeeze you in. There you go. We got you now. So there's 1, 2 twos. There's 1, 2, 3, 4, 5, 6 threes. There's 1, 2, 3 fours. There's a 5. There's a 6. There's no 7s. There's no 8s. There's a 9, and there's a 10. Now, when you look at this data in the form of a frequency table, it's probably better than this, but when there's lots of numbers, it's a lot better to have it in this tabular form, right? This frequency table format. Can you see that I can look at this and it's pretty easy to see that the most common number of siblings is 3, right? 6 of you, compared to any of the other numbers. That was our most common. I think if I look at it, would you agree that the pattern kind of goes up and then it kind of drifts down the way? So there is a kind of building up quite early on to the biggest number, and then less and less and less and less and less, and then it kind of, the end kind of trails off forever. So I get some kind of visual on what that would look like. So this is this table here is called a frequency table. Now, I think when they give you questions in WebAssign, it's a little bit clunky, because it would be really nice, at least the version I saw, it'd be really nice if you just have a table where these numbers were given and these were the boxes that you just typed in 2, 6, 1, 3, 0, 0, 1, 1, right? But I think it kind of does it as little funny individual boxes, you know, and it's kind of a little bit messy. That's just a problem with the way the software works. In real life, this is what a frequency table would look like, right? Cool. Now, frequency tables, cool. How do you convert this into a histogram? Well, basically, along the bottom, you put, in this case, whatever it is you were counting. I'm counting the number of siblings, right? And vertically, you always make the vertical one your frequency. And then you have, what, 2 to 10. So you go, there's 2, there's 3, there's 4, 5, 6, 7, 8, 9. Obviously, much neater than I'm doing it. And then 1, 2, 3, 4, 5, 6. And you go, where it is, 2 boxes up, 6 boxes up, 3 boxes, 1 box, 1 box, blank, blank. That's meant to be 9 here, and there's 10. And there's your picture. And can you see that little climbing up and then drifting away kind of shape that I was talking about? Right. Builds up, drifts away. So are we comfortable that if someone gave you a big list of numbers and they asked you to create a frequency table, that it's just a matter of counting how many 2s, how many 3s to build this, and then from there you'd get a histogram that would look something like that? What typically happens in the homework is they give you like 4 or 6 pictures, and one of them looks like this, and that's the one you tick. So when you do the homework question, you will have to draw this on some scratch paper, right? But when it comes to answering the WebAssign, you just pick picture C because it looks like yours. Right. Now, a couple of things that you might want to think about is that in these numbers here, 1 box represents 1 would be a pretty reasonable vertical scale. But can you just imagine, for argument's sake, that that was 20 and that was 60 and that was 35 and 17 and 16 and 12 and 17, things like that. You wouldn't really want to choose a scale of 1 box represents 1, because wouldn't you run out of paper vertically? So your vertical scale may have to change. You may have to go 2, 4, 6, 8, right? Every box is worth 2, or 5, 10, 15, 20. Normally, vertical scales should be done in units that are comforting to humans. Let's put it that way. 2, 4, 6, 8, I'm cool with that. 5, 10, 15, 20, not a problem. 10, 20, 30, 40, cool. 20, 40, 60, really cool. 17 34, 51, 68. Not a good scale, agreed? Brains don't like weird vertical scales. So your one box should be in some nice number, right? 2s, 5s, 10s, 20s, 50s. 25 is okay, but 20 is probably better. Big enough to show the whole thing, but not so huge that you spend forever drawing it. There's some kind of sweet point between those two extremes. And that's a frequency table. Now I'm making up another, this is my second example. I guess I should call it example 2. And in the second example, I'm going to use the same data, 2, 3, 4, 5, 6, 7, 8, 9, and 10, which is cool. And I'm going to use the same frequency. I'm just going to have a third column. Right, and this number was 2, 6, 3, 1, 1, 0, 0, 1, and 1. And what does that add up to? That actually now adds up to 15. 2, 8, 9, 10, 11, 12, 13, 14, 15, right? So 15 is our magic total. And the new column is called the relative frequency. And the way you get the relative frequency is you take 2 and divide it by the total, which is 15. But you don't typically leave it as a fraction. You turn it into decimal. So I'm going to go 2 divided by 15. And I'm going to round off to 2 decimal places. So it's 0.13. And the next guy is 6 divided by 15, who's 0.4. The next guy is 3 divided by 15, which is 0.2. The next guy is 1 divided by 15, and this is roughly 0.07. So will that one be. Those are still 0, and there's a 0.7, and there's another 0.7. So when you do a relative frequency, you don't use the raw data, which is 2, but you convert it into a fraction that's converted then into a decimal. Although we write 0.13 down here and we write 0.07 here, do you know that that's actually 13% as a decimal? So 13% of the people in our class had a brother or sister, right? Their sibling count was 2. 20% had a sibling count of 4, and whatever, 7% roughly had a sibling count of 6. So this relative frequency, we turn them into decimals, but in my brain, I see percentages, right? So I see that as 7%, even although it does say 0.07. Now, what does that look like? Well, it doesn't look anything different, really. I'm not going to do the whole table, just kind of a starter for it. You just have to have a different kind of scale. 0.1, 0.2, 0.3, 0.4. Do you see that my vertical scale, my relative frequency scale, which is this one, my number of siblings along here, do you see that it has to now represent decimal values? In this case then, 0.13 would be somewhere about here, 0.4 would be about here, 0.2 would be about here, 0.07, I'm guesstimating it somewhere about here. And can you imagine me doing the rest? If you look at this picture and you look at that picture, shouldn't they look the same shape, maybe different heights, but the same up and down shape? Because aren't they really showing you the same information? One is raw data and the other in terms of relative frequencies. You might wonder why we bother to have relative frequencies. It's quite difficult to compare 2 frequency tables if one frequency table has twice as many people in it as the other. Can you imagine there was 2 classes and one of my classes was your lot, right? And the other was a much bigger class, right? Like there were 40 people in it. if you just looked at the raw data, wouldn't it be hard to compare them? Because a class that's twice as big, shouldn't it be twice as many siblings, 3 siblings and 4 siblings? But if you convert them into relative frequencies, aren't you comparing like with like now? You're 20%, I'm 20%, that's an equal match. So I can look at those 2 classes and say, yeah, they're looking very similar. Or, oh, that's unusual. Why has one class got a lot of, 1 and 2 siblings and the other class has a lot more 5 and 6 siblings, right? There's some kind of difference in patterns there. So that's why we need a relative frequency.
Quick question about the histogram with the decimals with the relative frequency. Do you typically put it in decimal, or can you put it in percentage?
I think the textbook wants it to be in decimal, so I would just stick to what they want. Otherwise,
right. Okay.
Later on, they might, I can imagine a question, what is the relative frequency for this? And there's a box, and you type in 40%, and it says, because you'll type in 40, right? And they'll say, wrong.
Right.
So to keep them happy,
Okay.
Think of the software as being a really stupid sister or brother that you have to be really precise about it, or else they pretend they don't know what you mean, right? And that might work. Okay, so are we comfortable about how to create frequency tables, how to create relative frequency tables from raw data? And you can certainly look at the histograms and get meaningful information. You could, for instance, be asked, what was the most popular number of siblings in your data? And in our question, it was, 3, I believe, right? 3 was the most popular. So now we're going to look into grouped frequency table. So in this situation, what we're trying to deal with is we've collected data, but it doesn't really suit individual counting. Now you might think, well, what kind of data looks like that? Well, we're going to use you lot if you want to share. And if you don't want to share, you don't need to. Or you can do what my sister did, and that's be 31. Once she reached 31, her next birthday, she was still 31. And that works. And it worked for quite a long number of years until her first son became 31. And then it became a little bit problematic. So she gave up counting at that point. She just said it's a birthday, and that was fine. So you can be 31 if you want to be, or you can choose not to answer. Now, I'm not doing the raw data here. I'm not going to go through each one of you and say, are you 22? Are you 23? If I did that, can you imagine how big this table is going to be? I don't know who the youngest is, but let's suppose the youngest person is 17, right? Wouldn't I have to do 17, 18, 19, 20? Then, when you get to me, 63, 64, that's my age, right? 65. If I did it that way, wouldn't I have a very tall table with mostly zeros in it and the odd 1 or 2? And the whole idea of having a table is to try and take the data and summarize it in a way that allows us to see what the heck's going on, right? Is there any patterns? What's the most common age group? So what we have to do here is we have to group the data into groups. So we're going to have age, because that's what I'm going to ask you. And then we're going to do frequency. And the age is going to be 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, and 60 to 70. Now, there is a convention about this interval. Do you notice that you use the same number in 2 separate groups? 10 to 20 and 20 to 30. The convention is, when you write an interval like that, it means 10 years old up to, but not including 20. So if you're 19 years and your birthday's tomorrow, you're in this group, right? So if you're 19 years, 364 days, right? You still belong in the first group. If you've had your birthday today and you just turned 20, do you see you now belong in this group? So that's how we organize. You might have thought, why don't we go 10 to 19 and 20 to 29, something like that? It doesn't work well with histograms when you try and draw the picture. You need a shared common number between one consecutive interval and the next. Second thing about group frequency tables, the intervals must be and should be in the same size. Some people cheat a little bit and have some intervals 20 to 40 and then the next interval's 40 to 50. I guess you could do that, but in mathematics we consider that bad form, right? It's not a good way of doing it. So we're ready for the questions. I'm going to have to go back out and in of this so I can see you all at once. Which reminds me, I am now about to take registration, so if you hold on a second while I do a screen grab. Okay, so that's everybody. Got 1 more %, Monty, you're good. That was easy. Right, okay, so I can now see you, so we're going to do the thumbs up. Oh, Rachel, you get your thumbs up already. You jumping ahead of the game here. Right, let's start from the top. 10 to 20. Remember, you don't count yourself if you're 20, right? It's up to, but not including 20. So how many of you are in that group? I got 1. Okay, moving on now. How many of you are in the 20 to 30 year bracket and want to take part in this survey? 1, well, I'll start from the top. 1, 2, 3, 4, 5, 6, yikes. 1, 2, 3, 4, 5, 6, 7, 8, 9. I make it 9. I hope I didn't miss anybody. Right, anybody in the 30 to 40 age group? 1, 2, 3, 4. Okay. Anybody in the 40 to 50 age group? 40 to 50 age group. We have 2 of you. 50 to 60 age group. And me, right? So can you see how the data was constructed? You say we do a grouped frequency table. Now, what that would look like in a kind of homework situation, can you imagine all your ages were written up here? You know, 22, 26, 33, 42, 17. If you're lucky in order, but not always. Do you know sometimes they jumble them up? Which really means you have to be careful, don't you? Have to scan through them and count all the 20-somethings, right? And then scan through them again and count all the 30-somethings. But you got this fella here, right? Now, what does the histogram for this
We're
fella?
not seeing your screen again.
I am not good at remembering that. There we go. So here's our data. So what we're going to look at now is what does the histogram look like? Well, along the bottom, as always, you're going to do age. As always, you're going to do frequency. In this particular case, the first group is going to be 10, 20, 30. Do you notice that I'm numbering the lines now? That's important. Okay. Now, the first group, what do we got? Oh, the biggest number I need here is 9, right? So I'm going to go, 1 boxes represents 1. I think that's a good scale. So for instance, 9 would be there, right? So 10 to 20, there was 1 of you, right? So 20 to 30, there was 9 of you. 30 to 40, there was 4 of you, which would be about here. 40 to 50, there's 2 of you, which would be about here. 50 to 60, nobody, and me. You see how that works? So you may get a question, make that, done. Draw a histogram, 6 pictures, 1 of them should look like this. everything that we collected from this class is essentially in here, but we have lost some information. Do you know this group here, this 9 people in the 20 to 30s? I don't know the makeup of that. I mean, it could be 20, it could be 8 of you are 21 and 1 of you is 29, right? Or any other permutation under the sun. So you do lose a little bit of information. You can't help it. On the other hand, when you do individual counts, don't you keep pretty much all the information? You don't lose anything. But experience tells us you can't always do a frequency table when data is very spread out and you don't have a lot of numbers, right? You just can't do it that way. Are we cool? Now, suppose we had some data and I wanted to create a group frequency table for it. And I'm going to introduce some terms here that we use. So,
excuse me, sir?
Yes.
I think someone had a question in the chat about that
tell me,
graph.
yeah, could you tell me what the question is and I'll answer it?
Oh, they just wanted to confirm that if you were 70 years old, you would not be included in this case, correct?
Yeah, if you were 70 years old, you would have to be in the 70 to 80 group. Remember, this only is 60 up to, but not including 70-year-olds. So a 70-year-old person would be down here, right, in the 70 to 80 group. So the number on the left you can use, the number on the right you're only allowed to be up to, but not including them. Hopefully that's answering their question. If you see that, can you tell me? The reason I don't see that is that when I'm on the white screen, I don't get to see anything except essentially my white screen and a picture of your faces. So if that happens again, feel free to do exactly what you just did.
Oh yeah, sure. I didn't mean to interrupt. Just want to make
Oh
sure
no, you did exactly what I want you to do. So that's not interrupting my book.
Okay, right. Great, thanks.
So let's pretend we've got some data and I'm randomly jumbling up the numbers. And it looks like that. And can we imagine as well, just to make things a little bit more messy, that there was, I don't know, maybe 50 numbers, right? And I want to do a grouped frequency table from all these numbers, right? How would I start the collection? How would I essentially create this table? Well, what you need for this table is, don't you need to know where to start? What's the first group? And the second thing you need to know is, how big do you make this group? We call these groups bins. Interesting name, but they call them bins. So I'd be asking, how big do you want a bin to be? In other words, how many numbers belong inside it? Essentially, if you take the small away from the big, this is 10. So this table is using bin size of 10. So each group has got essentially 10 numbers in it, roughly, right? Now, in this world here, I need to know where to start. So if you want to know which group to start on, so let's suppose that this was something age and frequency. So we just went to a street and we found the age of everybody who lived in that street. And it's a small street, right? There were only 50 people lived in it. And these are the various ages. So there's our baby today. She'd be there, right? So the smallest age group is 1, right? And the biggest age group is 82. Let's say we scanned through the numbers and we figured that out. So I'm going to get a fella called the range. And the range is the difference between the smallest and the biggest. So in this case, it's about 81. So far, so good? Now, from the smallest number to the biggest number, I've got a range of 81. And I have to figure out from that information what my first group's going to be. Well, I know my first group has to have a 1 in it, because that's the smallest. I know that my last group has to have 82 in it, because that's the biggest. And now I have to figure out how big to make my bin size. Well, you take this guy and you divide them by roughly, very roughly, 7. Now you might think, what the heck is 7? 7 is just a made up number. We want a table, a grouped frequency table, to have roughly, very, very roughly, about 7 rows in it. Right? Now you can have 6 rows in it, you can have 8 rows in it, you can even have 9 rows in it, but roughly about 7, right? Now if you do 81 divided by 7, you are going to get your beginnings of how big to make your bin. And the answer I'm getting here is 11.5. That is not going to be the bin size, but it is going to be the guy that's going to help me get the bin size. What you then do is you turn it into a nice bin size. Remember we talked about vertical scales. Human beings like certain numbers more than others. If you're going to do a bin size, collect things in groups of 5, groups of 10, groups of 20, groups of 50, groups of 100, right? Can you imagine that there are certain numbers that just look pretty to the human brain? So I picked the nearest nice looking number to 11.5, and the nicest number I got was 10. Would you agree it's pretty close to 11.5? It's not bang on, but it's pretty close. Great? Now, you start with your group here. And so your first group is going to be just born to 10 years old. And then 10 years old to 20. And then 20-year-olds up to, but not including 30. And if I'd planned this ahead, I would have done a much better job. And when I finish on whatever group it would take to get the oldest person, so my last group would be 80 up to 90. Are you happy about how I decided to create the groups, the bins, for my grouped frequency table? You find the range, you divide it by 7. This number is a guide to how big your bin is. And then you make it a nice number. I'll give you some examples. Suppose I did the range and it ended up being 47, right? Oh, sorry, not 47. Suppose I did the range and I divided the range by 7 and I got 47. So what would that be? That would be, hold on a second, I'll tell you what you got. 47 times 7. I got 329, right? And I divided it by 7 and I got 47, right? That's this magic number here. Right? What do you think the interval size for a 47 should probably be turned into?
Would it be 50?
Yeah. So depending on who the smallest number is. So in this second example here, can you imagine maybe the smallest number was 27, just for argument's sake. Then my first group would be 0 to 50, then 50 to 100, and then 100 to 150, and then so on until you finished, right? What about if it was 127 was my smallest number? Can you imagine that might happen? I've got a big load of data, and the biggest to smallest had a range of 327. I divided by this just made up number 7, and it allowed me to decide that. Would I use these two guys? Would I need 0 to 50 and
No.
50 to... I don't necessarily need them. So couldn't my table quite...
But you would still use 50 as the bin size, right? You just
Oh
put
yeah,
these little
still
first
use
two bins.
50. Yeah, still use 50. Typically you should start at the group where the smallest number lives. And it might be 0 to 50, it probably would be, but it might not. It might be, you know, you don't need anything until you get 100 and 150, right? Because that was your smallest number. So that is what you would call, right, the way in which you approach how to create a grouped frequency table. You need to know the smallest number, you need to know the biggest. So that means scan through the data, find the biggest and smallest number, get what we call the range, right? divide by this magic number 7, and whatever that number is, use that to decide on your bin size. So you might decide in this case, I think 50 made sense. In this case that we just did, I think 10 makes sense. Do you see sometimes you make it a bit bigger and sometimes you make it a little bit smaller? If you stick to that rule, you will probably end up with somewhere in the region 6 to 9 rows of data, which is a pretty good size for a group frequency table. It's not too big where there's just too much zeros and nothing happening. It's not so small that you can't really see anything because everything's in, imagine you grouped them in such a way there was only 2 groups, right? 0 to 50 and 50 to 100. If I did that with our class ages, would you agree that there'd be virtually no information left in the picture? You couldn't really tell much. And so that's our trick. Are we good with that technique? Any questions about that before we go and maybe look at some of the homework questions to see how they're phrased so we're in the same place? Okay. Going to go out. I'm going to go, is that the only chat we have? Yeah, I can see your comment. Okay. So if you do not have the ability of audio, feel free just to nip in and say, before I continue, hey, could you tell me this? And I'll do that as well. So hopefully I have set this up in such a way that I can do it, but who knows? Okay, I need to close that window because it's no use to us. Try another one. What's this window look like? Oh, that's good. Are you looking at WebAssign page?
Yes.
You are? Okay, so we're going to look at section 2.1, which is essentially what I'm doing right now. Eventually, here we go. Are you seeing the questions?
No.
You're not? Okay,
Yeah.
so that means I have to go out and in
Yeah.
for a second. So I'm going to go out and I'll go back in, and this time you should be seeing it. Are you seeing the questions now?
Yes.
Right. So it looks like the questions. Here we go. Right. I'm trying to find a question that wasn't. Oops. Let me take out the solutions. It's very distracting if you see the answers. Okay, this is a kind of numerical one. So a data set of whole numbers has a low value of 20 and a high value of 82. Find the class width, right? The class width is bin size for the frequency table with 7 classes. There's our classic guy. So I'm just going to verbalize this. If you take 82 and subtract 20 from it, what do you get? 62? Agreed? And if you take 62 and you divide it by 7, you get something like about 8.8, 8.9. So how do you think I'm going to group this one? What do you think 8.9 would turn into as a nice bin size, as they call it, a class width?
Bin of 10.
Yeah. Now, since the first group has a low value of 20, can you imagine that I would start at 20 and finish at 30? That makes sense? And then the next one, I would start at 30 and finish at 40. And that's how I would continue. So I'm assuming that if we do this right, I hope we do, this guy's 80 and this guy is 90. And that would be my last group, 30, 40, 50, 60, 70, perfect. If you imagine the other numbers, do you see how that's going to match? And that's what your solution would look like. And in here, you would be saying, I'm going to use 10. So try to avoid bin size or class width size of 7s and, oh God, 8.2. Who ever would ever want to use that? But, don't use things like that. Try and use, nice numbers like 5, 10, 20, 25, 50, 100, whenever possible. Are we cool about that one particular question? Right. So I'm going to wind back a little bit. This is just a random question. A data set has values ranging from 10 to 50. What's wrong with using these as your frequency table? And looking at it superficially, it's got everything you'd expect, yet it is wrong.
It doesn't include the 50.
It doesn't, does it? Remember that last group means 40 up to, but not including 50. So do you see you have to go through this to figure out what is wrong with it? So let's see which one of those sentences. Each value must fall into one class. Some data does not have a class. That is their way of saying it doesn't have 50 in it. Do you see the phrase in a kind of vague kind of way, right? We're comfortable with that type of question? Now, if we wind back, do you see in this case here, 10 to 19, 20 to 29, do you see they've done the classic, what some of you thought a grouped frequency table might have looked like, right? And what is wrong with this then? Why are you not allowed to do this? Well, each data value must fall into one class. The classes have overlapping values. Well, that's not true. The class widths are too wide. That's not true. Each data value must fall into one class. The data value is 50, does not have this class. Oh, well, that is actually true. Well, there is actually something else wrong with that, but that's the only one that they've gave me in this list that's wrong. I would never, ever use this. Always use this. Okay, so next thing we're going to do is look at some histograms. And what you've got here is someone who's broken my rule of doing weird intervals. Would you agree that 20.5 to 24.5 is just one ugly interval grouping? I mean, it works, it's right, but would you agree it's very hard on your brain to get a feel of what each group is? Right? That's not what the problem is. They're just saying, hey, work with it. But we're going to look at some examples of histograms, and in particular, we're going to look at how you describe shapes of histograms and things called outliers. So I'm going to leave this guy for a minute, and I'm going to jump back into our notes, and we'll show you some of the types of things that can happen. Now, typically when you draw a histogram, you're going to draw rectangles. But for convenience and speed, I'm going to draw histograms that look like that. And I want you to imagine that there's basically rectangles here, but for speed, I'm just drawing rough curve through the guys. So can you imagine that is meant to be a histogram, but for speed purposes, we can just draw its general shape. If you want to draw the general shape of a histogram, do you know you just put a dot at the middle of each of the heights, and then you draw a curve through it, right? That's essentially what I'm doing. Are we okay with that shortcut? So I don't have to keep drawing lots of rectangles, right? So, first thing is some histograms are unimodal. Some histograms are bimodal, and some histograms are multimodal. So what does that mean? If your histogram has got one hill, it is unimodal. Some histograms have two hills. They're called bimodal. You know, bi like in bicycle, two wheels, right? You know, anything that starts with the, I think it's a Latin derivative, bi means two. I'm trying to think of bicentennial, every 2 years, right? Every 200 years, I should say, or 200 years has gone by. Try to think of bi, another bi. Can't think of one off the top of my head, but bi means two, unicycle means one, and then multimodal. Multimodal could mean 3 hills, 4 hills, 222 hills. We don't continue the naming process typically after 2. You could, well, you tell me, what do you think you could call a treble hill in the notation or the naming that we're using here? Uni is 1 hill, bimodal is 2 hills. What would a 3-hill histogram be called?
Tri-hill?
Yeah, trimodal, right? Right. And then I guess quad modal and then pent modal. You can see why nobody's going to do that, right? You're either got 1 hill, unimodal. It's worth it for 2 hills because bimodal can sometimes be quite interesting information. Multimodal just means there's lots of hills. You can get each of these shapes depending on what your data is. For instance, see if you give someone an exam or a class exam, you know very often the shape of all their scores is unimodal. And roughly the average score is where the hill is. Now, if you have 2 hills bimodal, you can sometimes get that data when you collect data from a population where that population is really made up of a mixture of 2 separate groups. To give an example, see if you went and did weights of people, weights of adults. Do you know that the men might be here and the women are here? Because men, adult men typically, not all of them, right? But aren't adult men typically going to be heavier than a typical adult female? That's just the way the human race is constructed, right? Men are fatter, bigger, taller, heavier, whatever you want to call it. So you might get something like that. You could have multimodal if your data was weather related. Can you imagine you got the highest temperature in a day and you collected it over a multitude of days? You might be able to look at data in the terms of, well, you know, in the winter it's this, in the summer it's that, and that could generate a data that looks like that. So that's our first naming system. How many hills does it got, right? Second naming system. Name is only used typically for unimodal, although we do give some flexibility here. Sometimes the data looks like that. Sometimes it looks like that. And sometimes it looks like that. Now, you can either all unimodal, right? At least the examples I've given. But isn't there a difference in the location of the hill and how the data is spread out?
Isn't the first one known as like a bell curve?
It is. It's one of its names is a bell curve.
Yeah.
Because it looks like a bell, I guess, right? The term that we're going to use, and that's correct what it is that we say that this is symmetric. So this histogram, we would say it's unimodal and symmetric. Now these two guys are unimodal as well, but this guy is called skewed to the, oops, almost put the wrong one in there, skewed to the left, and this one we say that it's skewed to the right, which might seem, the right and leftness might seem wrong to you because people think it's where the hill is that gives you the name, but it's not. See this piece of the curve that drifts off this side here? This is called the tail. And you're skewed to the right if it tails off to the right. And you're skewed to the left when it tails off to the left. And you just have to get used to that's how we name these things. So skewed to the right, skewed to the left, symmetric. So we now have another term that we can use to describe a histogram. So imagine I went and said to you, I have got a histogram of the ages of some people in one of my classes. And it's unimodal, and it's symmetric, and it's centered at 30 years. Can you visually almost imagine what my histogram looks like, even although the only thing I've told you is words? Centered at 30, unimodal, symmetric. Can you kind of imagine this guy with a 30 right there? If I said, oh, and by the way, my other class, it's unimodal, but it's skewed to the left. Wouldn't that mean there's a lot more younger people in that class? Skewed to the left. And my third class, it's unimodal, but it's skewed to the right. Wouldn't that indicate that there's a lot more older people in that class? So we have the ability now to describe histograms in terms of modality, how many hills they have, and now an extra phrase, skewedness. Skewed left, skewed right, or symmetric. Now, nothing is going to be perfect in real data. So you might want to stick the word roughly in front of all of these, where it's roughly skewed to the right, roughly symmetric, or roughly skewed to the left. And that will get you through all the kind of, yeah. And you are allowed to have small inconsistencies. Can you see I've got a little kink at the end? And that kink might just be that everybody either side of it was 3 and that kink was a 4. So it went 3, 4, 3, 3, 2, 1, nothing, right? Do you know that kink is hardly worth calling a hill? So it's roughly unimodal and skewed to the right. So can you see in the real world, you don't get perfection. Everything doesn't go up to one hill and then drift down gently. Can you imagine it kind of ripples on the way down? Not really worth calling a hill. So in a big extreme, do you imagine it kind of went up like this and kind of wobbled down like that? And that would really still be considered unimodal. And wouldn't it really be considered skewed to the right? And those funny little wobbles, you know, that tiny little bump there, it's not really a true hill. Don't you have to be noticeably up and then back down again? So that is definitely bimodal, right? Pretty cool. Now, one last thing to add to how to describe in words some of the features that a histogram have. And this last term is called outlier. Anybody ever heard the term outlier? You know, I've taken a class where they talk about something that's exceptionally different from the others. It's very often called an outlier. In many situations, an outlier it can be caused by just an error in your experiments, right? Or an error in measurement. You know, people are measuring the weights of things, and for one of the weights, they forgot to put the decimal point in. So all your normal data is 5.1, 5.9, 6.2, and then one of your data is 49. And that would be exceptionally large, and that would be considered to be an outlier. Right? So what do outliers look like? So I want you to imagine that you have a symmetric unimodal data, and then nothing much happens. So let's pretend that this is a class where it's unimodal, symmetric, and the center's around about 30, right? And let's say it tapers off at 50, right? And then we have a 98-year-old in the class. So can you see that there's a distinct gap and then there's this one little person sticking out like a sore thumb. This is the person that we would call an outlier. Now, it's probably a little bit better if I draw a histogram. So can you imagine that you did a histogram of your data and it looked like this, and then you got a little rectangle over there. Now, this is a large outlier, but can you imagine that you could have a situation where the little bump was over here, and this would still be an outlier, right? It would just be a small outlier. So an outlier is something that's exceptionally different than the rest of the data. So we can now look at a histogram and talk about unimodal, bimodal, multimodal. If it's unimodal, really should stick to just unimodal situations. Can't we also talk about skewed left, skewed right, symmetric? And back to any kind of histogram, for any kind of histogram, can't we talk about outliers as well? In the sense, this has an outlier at 98, or this has an outlier at 2. You can't, there is a problem with this outlier problem. Right, I'll use this guy. I think if I went and said to the class, does this guy over here look like an outlier? You'd all nod your head and say, yeah, he's an outlier. Let's move him to here. So that one's not there. Is he an outlier? Yeah, probably, but not as certain. Okay. Now, suppose I put him here. So there's only like one gap and then there's a rectangle. Would you agree that that's not exceptionally different from the rest? So that guy's not, and let's say this guy is. Can you see somewhere between here and here, there's a gray area? And so it's not yet anyway. We'll show you later on a numerical way of deciding you're an outlier or you're not. But right now, it's a kind of judgment call, isn't it? That number away on the right-hand side, it's an outlier. But as that number starts moving in, there comes a point in time where it's close enough to the rest of the data to no longer be called an outlier, right? It's just a big number, but it's not that exceptional. It's not fair for you to get a question where they give you a grey area. So I suspect that when you get an outlier, it's going to be, yep, that's an outlier, right? You won't have to say, not so sure. Are there any questions about that? Are we comfortable about unimodal, multimodal, bimodal, symmetric, left skewed, right skewed, and now outliers?
I have a question about the outlier. Now, if the outlier is something that's like pretty much different and away from where the original skewed is that number going to be either higher or lower, or it's just something that's just going to be sticking out like a sore thumb?
Well, in a way, what you said sounded like you were saying the same thing, because it will be higher and lower. Outliers are at the end of the data, and they'll stick out like a sore thumb at the end of the data. Now, I think I might be able to think of a situation where what you're talking about might be a case. Can you imagine I've got some data where there's like two distinct hills, men and women, and then there's a little guy in the middle on his own son. Now, I guess that sticks out like a sore thumb, but he is not an outlier.
Okay.
Outliers live in the big and small world, right? So I guess now I thought about it, you're sticking out like a sore thumb might not be a good description. Sticking out like a sore thumb and you're really big and small, right? Now you put them together, now it's an outlier. That makes sense?
Yes, that makes sense.
Okay. So what I want to do now for a few minutes is, because I want to go over some of my notes, because they've got some good pictures and we can look at some of the ways in which you can describe histograms. I'm going to have to zoom about a little bit as always. So here we go. Has anybody got a bad joke for us while I'm getting this set up?
I do.
Cinderella
Okay, go
story.
for it. What's your joke, Rachel?
All right. What does a thesaurus eat for breakfast?
I don't know. What does a thesaurus eat for breakfast?
A synonym roll.
Oh,
Isn't that
that
great?
was so well done. Yes. Oh, never heard that one. Anybody got another one? I'm almost there.
I've got one.
Go for it.
Why isn't COVID prevalent in Antarctica?
I don't know. Why isn't it?
Because it's isolated.
Ice. Oh. Oh, God. What did the big chimney say to the little chimney? Don't know? You're too young to be smoking. Yeah, that's all I got. Okay. Okay, I'm ready now. So what we'll do is you like that one, Mary? You're smiling at that. God, yeah. You're easily pleased. Right. So these are some notes that you'll get in Canvas. These are my notes. Here is a whole set of data. And can you see that the data doesn't vary too much, so you can count each person individually. And then can you see what the histogram would look like? And here is some data of some rainfall. In this case, the data, although it's decimal, does vary a lot. So 0 to 1 inch, 1 up to 2, 5 up to 6, and here is what it looks like. And can you see that you go 0, 1, 2, 3, 4, and you create its histogram, right? Here is an example of a dot plot, which is essentially just a visual person representation of data. And skip that stuff, we'll come back to that later. Skip all that stuff. Right, here we go. Right. If you look at this histogram here, can you see that it's bimodal? Would you agree this is unimodal? Here's a term I haven't done because I don't think the book even uses it. But you know, if the data doesn't have any real distinct hills or valleys, it's pretty much every number is pretty much the same as every other number. You know, there's some variation. And we would say that's just uniform. Now, symmetric, skewed right, skewed left. Right, let's look at this data here. See this one here? Right. I would start by saying this is unimodal. There is one hill. Would you agree that that's a significant gap to this data? And do you know what this data, I think roughly there's 3 people in this interval, or this number set, right? There's 3 people. So an outlier can have company. Now it doesn't need to be one on its own. Can't it be 3 exceptionally big numbers and they're all outliers, right? So that would be considered an outlier. Now, if you turn this picture on its side, which is a bit hard to do in your brain, but can you see that this particular one looks to me like there's 2 distinct hills? And there's a gap in the middle, which we don't worry about. I guess the only thing I would say then is that this particular shape is bimodal. And here's the question, that dot at the end, which looks to me like it's roughly about 175, would you count that dot at the end as an outlier?
I wouldn't.
Right. And you know, some of you would say, yes, I would. And you know, I would say both answers are correct, because isn't that a kind of subjective call? Do you think it's far enough away from the rest or not? And I think in this case, you could argue equally validly that yes, it is, and no, it's not. Right? I mean, for instance, isn't the gap between the 2 hills much bigger than the gap between here and here? So that might be your argument for why it's not an outlier. You might argue that this is a significant space and it's really big. You know that and it's really big is important for an outlier. And that's why you might say, yes, it is one. I think if I put the dot away up here, right, so imagine the line continued and the single dot was up here, I think we'd all agree that it was an outlier. And if I start bringing the dot closer, so if I move this dot to about here where my mouse pointer is, nobody would say that was an outlier. But I think this guy here is probably right in the middle of that grey area, isn't it? If we moved it a little bit further away, I think everyone would agree it was an outlier. And I think if we moved it even a little bit closer, none of you would say it was an outlier. So outliers are a little bit subjective. I don't think unimodal or bimodal, for the most part, is that kind of issue. Any questions before we start looking at some of the homework questions? Are we good? Jenny, you look puzzled. Are we good?
I'm good.
You're good. So it's not puzzled, it's thinking, right? That's your
Yes.
thinking face, right?
I'm thinking about that homework assignment in which I kept getting it wrong and I thought I was doing it right.
Is it to do with outliers?
No.
Oh, okay. Well, I don't know what that question is for the time being. I guess it'll be a mystery to me. You can always ask me later. Let's see if I can.
I do have a question about homework assignments, about the previous homework.
Uh-huh.
How do you tell that it's 100% that you completed your homework, like that you're gonna get it? That's my like paranoia. Like, is it done? Is it done?
I believe you can tell me because the people do it. I don't quite see it. When you do a question, doesn't it just say, yes, you're right? There's a little green tick or something. Is
Yeah.
that what you get as your feedback?
Yeah,
Yeah.
but like at the end, it say 80% or 80%. So,
Okay.
you know, it says the percentages on the side.
Yeah. Well, if you answer each question and you've got a number or a box or a yes, whatever the answer is, you're done. So
Yeah,
if there's
so-
12 questions, you make sure you answer 12 questions and you're finished.
But sometimes I'd go back and hit the green question and change it. I'd be like, oh crap, I just had that right now. I changed it. I'm like, oh crap. Because, you know, I can't tell, did I?
Well, you get 3 shots. So if you do the right answer and then you change it to the wrong answer, you've got 1 more shot to change it back to the right answer and then leave the damn thing alone, right? That would be
Yes.
my advice.
It's very
So don't second guess yourself. If it says check green, you are right, right? Don't go back and think, maybe I could do a better version of right. Right? There's only one right, leave it alone. Right? That would be my advice. So don't get too caught up with that. Where am I trying to go now? I'm trying to go back into here. That's where I'm trying to go. And I'm going to, in a few minutes, you can't see this, I know, but well, I don't think you can see it yet. We're going to look at some okay, we're going to, I think I'll start here, right? So I'm just going to go out and back in again so you can see what I want you to see. And here we go. Right, so if you're looking at this histogram, somebody should tell this person that in statistics you are allowed to choose better intervals. I'm going to criticize this interval again. I mean, 8.5 to 12.5, that is just ugly. I mean, why didn't they at least say 8 to 12, right? Would you agree that would be a better interval, right? But I think what's happening here is that the computer is just generating them. And so the computer ain't, you know, human beings can make kind of calls on how pretty, for want of a better word, something looks. But a piece of software, 8.5 to 12.5 is just as good as 8 to 12, right? It doesn't think there's any issue with that. So it's been programmed to do that. So I'll just live with that and let it bug me later. Now, in this diagram here, down here, we are going to put in our information. So class boundaries. The first class boundary here is 8.5. Oops. 8.5. And it finishes at, what, 12.5? And that's 12.5. And the frequency, I'm glad they put that number there, but I think I could read it off anyway. Would you agree it's 6? So can you see that from a grouped frequency histogram, as I have here, I can make a grouped frequency table, right? So from this picture, I can make a table. From this table, if you had a completed table, couldn't you make a picture? Right? They're basically the same information. The histogram is visual. The table is more like a table, right? So it's a picture or a table. Totally, yeah, I'm good. 1, 2, 3, 4. 1, 2, 3, 4. Looks like I'm not going to use the last two. Well, that's probably the computer again. Just because there's 6 rows doesn't mean they're going to be 6 numbers. If I did want to keep going, I guess I could, but wouldn't I put 0 and 0 in the last two? Because there's nothing over here. I would probably. Question?
It says to use the class boundaries given right there. So since those numbers are on the graph, half of that would just be zeros for the frequency.
Yeah, I would think so. If they say use them all, then that would be it. I'd have to work my way through the rest to find out who these two are, but I'm pretty sure that this one is 24.5, and that goes up to what, 28.5? And this last one would be 28.5, and that would finish probably at 32.5. Have you noticed that all these intervals have a width of 4? All these bins are 4 units, and all you do is take 12.5 and subtract 8.5, right? 4. So you just keep going. Add 4, start at that number, add 4, start at that number, add 4, till you don't go any further. Now, what's question 9 got? The following data represents salaries in thousands. So 60 means 60,000. It's a small company. Most of the data has been sorted in increasing order. That is nice of you. Make a histogram with these class boundaries. Oh, come on. They're just doing that to annoy me, aren't they? One of those 4 pictures is going to be the histogram. I'm trying to look at which one of those 4 it's likely to be, and I have made up my mind. Which one of those 4 pictures is going to be the correct histogram for this data? So it's not a trick question, but it is a kind of yucky question. One of those 4 pictures you can do just by looking at the numbers. Is it number 1, number 2, number 3, or number 4? I'll take a volunteer.
Number 2.
I hear number 2, and I think I heard another one before that. What was the other choice?
The first one.
Yeah. Well, let's look at the difference. If you take everybody from 53.5 to 99.5, aren't you actually using everybody except that last guy? And then there's nobody in the middle, and isn't that last guy in this interval? Now, as far as, excuse me, as far as intervals go, this is not their question. I wish it was their question. Would you agree that is a horrible interval size? Right? I wouldn't choose that interval size. I would choose something much better. I certainly wouldn't start at 53.5. I'd probably start at 50. And I might go 50, well, what might I got? I might got in 20s or something, like 50 to 70 to 90 and something like that. The last number would be an outlier, of course. Now it says, look at the last data value. Does it appear to be an outlier? Okay, so we'll just look at this picture. I know it's a horrible histogram, but would you agree that that guy is significantly different than the rest? So, yep, he's an outlier. Now this interval looks interesting. If you take away the 280 number, right? If you remove this number from your data and you create the histogram that you have with this number, ignoring the fact that they don't know how to make good intervals at the bottom, one of these 4 is going to be your histogram. Right? One of these 4 pictures is going to be the histogram that you would get if you used all these numbers with the exception of 280. So you might think to yourself, how will I know which one it is? Well, let me do that Sherlock Holmes thing. Do you know where you eliminate all the bad things and what's left must be the answer? So without even doing any work, I am going to eliminate this picture and I'm going to eliminate this picture, right? These two. What is clearly wrong about the way these pictures are written?
The axes.
Right, which axis has got the problem, or what axis is wrong?
Probably switch the frequency and the salaries.
Yeah, and do you know this guy is 62.5? It's not. Shouldn't that be how many people were in the range from here to here? So I'm kicking these numbers out. Shouldn't frequency be how tall the rectangle is? So it's either this one here, right? Or it's this one here. Great. Now, they use the same horrible interval on the bottom. And this one goes 7, 11, 5, 6, 6. And this goes 7, 8, 5, 9, 6. Now, I can't tell looking at these two which one is the right one and which one's the wrong one, but I definitely know these two are wrong. So if I wanted to know which one was correct and which one was wrong, what I would do is I would pick one of the rectangles, one of the intervals, and see which one actually was correct. So I'm not going to pick this one because they're the same, and I'm not going to pick the middle one because it's the same, and I'm not going to pick the end one because it's the same. So how about if I pick 62.5 to 71.5? Do you see that interval from here to here? Now, according to this rectangle, shouldn't there be 11 people in that salary range? And according to this histogram, shouldn't there only be 8 people in this salary range? So 62.5 to 71.5. You scan through here and you count all the people from 62.5 to 71.5. Okay. So 62.5 starts here, right? And 71.5 finishes here. So if I count all of them, I bet you it adds up to 11, so it's this one. And that would be my answer. Now let's see what's happening here. Histograms of random sample data are often used as an indication of the shape of an underlying population. The histograms on below are based on random samples of 30, 50, and 100 from the same sample population. So what you did here is that you went out and you asked 30 people something and you got an answer. And the sample size was 30, right? And then you asked another group of 30 and you got the same answer. So it might be, I stop 30 people in the street and I get your age. Oh, the average age is 22. And then I stop another 30 people, somewhere else and I get their average. And this is essentially the result of what a 30, what a 50, and what a sample of 100 would look like. And using the midpoint labels of these 3 histograms, what would you say about the estimated range of the population data from the smallest to the largest? Interesting. Okay, now they're not giving us an awful lot of information, but would you agree that this guy here is at 7? And would you agree this guy is at 12? So won't the difference between the smallest to the largest be 7 till 12? Now, in this case, you got in 7 to 12, and in this case, you got 7 to 13. So there's a little bit difference on the last one, right? Based on the completed table, select the most reasonable estimate for the range of population. Well, if I said 7 to 12, in this case, 7 to 13, would you agree that you could probably pick that one or that one, depending which one you think is more realistic? And then they go into some stuff I don't want to do. And now we're going to look at a new kind of graph. So we know how to do frequency and group frequency. We know how to do histograms from those shapes, right? We've looked at those. We're now going to look at cumulative frequency graph. Right. So let's have age and frequency. Probably age is a bad choice. Number of siblings, let's do that one. Number of siblings and frequency. So there's 1, there's 2, there's 3, there's 4, there's 5. So a different class, I asked them the same question, and the data I got only went from 1 to 5, right? There wasn't anything exceptionally big. And there was 5 of these, there were 8 of those, there was 4 of those, 2 of those, 5, 13, 7, 8, 9, and 1 of those, right? So that's what a classic normal frequency table looked like. So what I'm now going to show you is a cumulative frequency table. And you have number of siblings. And you have cumulative frequency. So you start off with 1 and there's 5 people. Nothing special about that. You then do 2. The cumulative frequency is 13. So that 2 doesn't really mean 2, it means 2 or less siblings. And there's 13 people who had 2 or fewer siblings. So if you go to the next one, 3. That doesn't mean how many people had exactly 3 siblings. This 3 means 3 or fewer. So if you add them together, you get what? 17. Basically, it's adding on each interval as we go through it. Can you see in this case then, the next answer is going to be 19. And then the last one, is going to be 20. So do you see how a cumulative frequency table is created? You start off with the first number is the same. But as you go through, do you see you continually just add the next total? So this 5 doesn't mean 20 people had 5 people in their family. It means 20 people had 5 or fewer in their family, right? So it could be 4, 3, 2, or 1. Now, what does that look like when you draw it? You typically would draw one of these, not with histograms anymore, right? I'm doing abbreviations here. What we got 20, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Can you imagine I was doing this in boxes? 1, 2, 3, 4, there's 5. And you would plot 1, 2, 3, 4, 5. One sibling, there was 5. Cumulative data on 2 siblings, there was 13. 3 siblings, it was 17. 4 siblings, it was 19. 5 siblings, it was 20. You see how that graph, that cumulative frequency graph is created? I mean, it's basically you join a whole set of lines together. Does that make sense? Now, if you do one of these, they do have some shapes that happen. Can you imagine the shape is a straight line? How do you think you might describe that to someone? How would you describe this cumulative frequency graph to someone? What word do you think we use? The mathematical word that means the same thing as a straight line.
Would that mean that that line is positive, like it's going?
Oh, yeah, it is positive. You're right. I don't think my question. Yeah, my question wasn't clear. What I was looking for is it's linear, right? So you would say this cumulative frequency table was linear. There's a lot of frequency tables that look like that. And I can't explain the name for this because I don't know where its name came from. But it's called an ogive curve. You ever heard that term? Ogive curve? Nah. You probably never will again. I just put that in because it has a name. There we go. Right. Now, when you look at any kind of cumulative frequency table, it must always be increasing. Would you agree the next number has to be at least the same value or bigger than the previous number? So if anybody ever draws a cumulative frequency table and it does that, you know that it's wrong, don't you? You'll be able to, you know, so if they gave you 4 pictures and said, which one of these cannot be a cumulative frequency table? Aren't you going to pick this red one at the bottom? That's okay, that can happen, that can happen, that can happen, but never that. Are we cool on that? Right, let's go back to the homework question then. And here is an example of that. And they've given you the data with all the little numbers on it. And you, oh God, tons of pictures, have fun. Right. We're getting, I think we're almost at the end of this section, which is good time for me. So here we have a whole load of data. It starts at 45 and it's random as heck. And it's going to say use 6 classes. So if you wanted to know how to find how big your intervals are going to be, class boundaries, midpoint, frequency, relative frequency, cumulative frequency, right? They're doing everything in this question, including class limits. Go figure that out. I'll let you look up the class limits. It's just notes in the textbook. Let's go and look at this one. This is question 12. Can anybody who's got better eyesight than me tell me the smallest number in that list?
45.
Right, I've got a candidate 45. Does anybody, I'm not saying she's wrong, does anybody see something smaller than 45? If not, we're going for it. Right, same question, but now, what's the largest number in that list?
101, or sorry, 109.
Okay, so we do 109. So you can't see this, but what I'm doing right now is I wrote 45 and 109, and now I'm going to get the range, which is 109, the biggest, take away 45, and to make sure I don't screw up, I'm doing it on the calculator. So 109, take away 45, I get 64. Okay? Now, they are deliberately making you break this guy into 6. Now, me personally, I don't like that question. Wouldn't you divide by 7 and make it look pretty, which is a kind of general rule? And sometimes you get 6, sometimes you get 8. Come on, let's go. That's my dog paying a visit. So back to what I was saying. That does mean that I have problems. I'm going to have to break my rule to keep them happy of having ugly intervals. To me, a nice interval would be 40 to 50, 50 to 60, right? Something like that. But I'm going to probably end up with really ugly ones. So what you can't see is I'm doing 64 divided by 6, and I'm getting the answer 10.7. Now, in a nice world, I should be able to make that 10. If I did make that 10, unfortunately, I would end up needing 7 intervals. Right, just the way the numbers work. And it's not your fault, it's not my fault. We'll have to just blame the book. It says, find the class width. So technically, the class width in this case is going to have to be 10.7. I'm not really satisfied with that, but I'm going to have to do what I can. Right, which means we are going to have, this is what happens when you let computers need near questions. Isn't my first group going to be 45 up to 55.7? I guess technically, right? can we pretend it's just bugging the heck out of me? Wouldn't that have been a much more natural number? Right. Tell you what, if you do that, I'm not going to mark you wrong, even if the book or the homework does, right? I don't want to go and do things that are not realistic. Right, so the next group then, based on my adjusted answer, is going to be 50 to 60, right? And then it's going to be 60 to 70. And so on
you're
and
saying,
so on.
oh, sorry. So
Yeah.
you're saying if we put that in, you won't
Yeah,
mark
if
it
I'd
wrong.
prefer you put that in and be marked as wrong, and I will just give you the point. I'll just go
Okay.
back in and give you the point for it. I don't
Thank you
see
for that.
any. It's a fault of the computer. This computer is generating this data randomly. When it does that and it says you have to use 6, they're really putting you in a bind here, because the interval, the class width, would have to be 10.7, and I just couldn't handle it. My brain was not going to accept that, right? So I'm going this way,
me too.
right? So human beings would never do that. We have flexibility. Wouldn't we say, hey, I can do 7 intervals, right? If I make it 10, I'll get 7. I can handle that, right?
Can I ask a
Okay.
question?
Yes.
When I was doing this homework yesterday, and I was looking in the notes in the book, it said to find the class width that you then compute the value and then round to the next highest whole number. So
It's a little bit better. So I guess
11.
11. I still don't like it. I mean, it's better than 10.7. But would you agree, what would that be? Well, you'd probably start at the smallest number. So if you were going to do what they just said. Now, I like this one. I know it misses the last number. But, I mean, just for aesthetic reasons, doesn't that look like a much nicer boundary size, right? But anyway, let's do the 45. If you add 11 to it, that's going to get you, 56? And off you go. I mean, so if you did it that way, I guess I'm going to just talk myself out of my brain, right, and so on, right? That's going to work, and that's fine. Now, midpoint. I haven't talked about the midpoint, but its name kind of gives you an idea of what it is. What's the midpoint of 45 to 56?
50?
Say again?
Oh, sorry. I didn't even know my microphone was on.
Oh, okay. 45 to 56. And the question is, what's the midpoint?
45 and a half.
Well, half. I believe it's that number. If you want the midpoint of two numbers, it's another way of saying halfway between them. So don't you just add them and divide by 2? So that would be the midpoint of this one. So I'm pretty sure that if you do the next one, it's going to be 61.5. And if we redo all the other guys, since I've kind of committed now to doing it their way, you're going to get, is it 72.5? I hope I'm doing this in sync. So the next one would be what, 77 to, that won't be 77, will it? Uh-oh, made a mistake. That's 78. That's 78, and that'll be 89. And that'll be 89. And this will be 100. And yeah, and this will be 100. And this last guy will be 111. And that is enough room, isn't it, to get the 109 in it. Do you notice that these guys here that I'm writing down, the midpoints, and I'll just finish them off and show you that there is a quick way of getting all these answers without having to do every single guy, adding them in half it, adding them in half it.
Don't you just add 5.5 to the lowest class boundary? So like 89, you'd add 5.5 and then you'd get the midpoint.
You know, you do that. And that's not the way my brain works, but that is perfectly correct. Tell you how my brain works, and it's just the way my brain works. Do you know how you get the first one? By adding them and halving it. And you're just saying, look, add 5.5 to this one. That's what she was saying, right? Works perfectly fine. All my brain does is, do you notice if you start with this one, isn't everybody else 11 more than the previous one? And isn't everybody here 11 more than the previous one? And is everybody here 11 more than the previous one? And isn't 11 the class width? Now, the next bit is frequency, and I'm not going to attempt to do this. Can you pretend it was 5, just for argument's sake? Right? Now, what would the relative frequency be? Well, 5 out of the total number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 6. 1, 2, 3. There's 70. So I guess you would do 5 out of 70. And that would be 0.07. Or they might have just written it down as a fraction. Who knows? They may have written that down, right? Which is the same thing, but as a fraction. Now let's look at the cumulative frequency. Can we just pretend that this is 12 and that let's just pretend that this is 20, just for argument's sake? 5 is your first one. What's the second, this next cumulative frequency going to be?
17.
17.
Yep, agreed. Oops. And the next one?
37.
Right. Now, see when you're doing cumulative frequencies, you don't need to add all the numbers again. Can't you just add the last answer to the next one? So the last answer here was 17, the next number is 20, so together you got 37. And if you do it correctly, shouldn't that last one be 70? If there's 70 numbers anyway, it should be 70. There we go. Now, one of the reasons I changed my mind, although it made my brain hurt to accept this interval, is that you need to figure out which one of these guys is your histogram. Right, because you need these numbers matched with these fellas. And you can see their histograms are built in various ways. And then they got the ogive. There we go. Ogive curve. I have no idea what it's called that. Here's another one where you basically fill in lower and upper and all that good stuff and relative and cumulative frequency. You do a histogram. And then they talk about which of these is your shape. Right? So you might do one and it's skewed right, in which case you would click that, right? If I look at all these shapes, no matter which one ends up being the right answer, what shape would you call that? Skewed left or skewed right? Just by looking at the histograms right now.
Skewed right.
Yeah. You see, try and imagine the curve. It goes up and then it tails off. Does it tail off perfectly? No, it's going to ripple on the way down. But its major shape is skewed right. And in fact, aren't all of these skewed right? So I'm pretty sure that would be the answer to that one. Okay, I'm going to use the questions that they've got. How much time have we got? We finish at 11, somebody reminds me, 11:30, 11:40, what is it?
I think it's 40.
40, okay. Right.
It's 11:25.
11:25.
11:25.
Darn it. Okay, you're getting the 30-second version of this, mostly because it's not too bad. At least I think it's not too bad. These are called dot plots. And can you imagine that every single one of these dots represents one data point? Right? And so it's a bit like a very primitive histogram. Can you imagine each one of these as being like a rectangle? And so you can look at this from this dot plot. How many states have 600 or fewer? Well, if you look at 600 or fewer, can you see there's only one dot there? Now, about what percentage of the states, there are 51, seem to have close to 800 licensed drivers per 1,000. Now, I think the word I'm having to watch here is close to. So I'm assuming that they're going to mean all these guys here. Right. Now, if that's what they do mean, won't the answer be 5 out of 51, which is roughly, what, 10%? Now, it says consider intervals 550 to 650, 650 to 750, 750 to 850 licensed drivers per 1,000. In which infield do most states fall? Okay, so if you did 550 to 650, it would be all these guys. There's not many of them. Then you do 650 to 750. Clearly, isn't that going to be the big group? Right. And here is some data. Tell me which dot plot it is, and we're finished. So that was